on actually four topics that are of importance to directed energy deposition. The first one really continues this broad general discussion of all of additive manufacturing. But once we finish the classification of AM processes and move towards laser additive, I'm going to focus in really on directed energy deposition, really for almost the remainder of the course. So with that, let's move to the topic. Additive manufacturing has for many years, really, since about 2000. So for the last 25 years, we have defined 7 broad categories of additive manufacturing process, and you see them all here. I'll walk through each of these specifically in a moment. But there are these 7 processes. The names have been developed again by the committee that deals with ISOASTM 52900, and these are the official definitions, and I think they're fairly good definitions for the various kinds of processes. So rather than dwell on this, let's jump in at each individual one, and we can talk some about the process, maybe what's good, what's bad about it. So material extrusion is a process where materials basically dispensed through an orifice and deposited. There are a variety of methods to do this. The most common is to use a thermoplastic material. Again, those of you that are familiar with these machines, it's PLA and ABS are the 2 common materials for material extrusion. Although there are others, there are high-performance materials that are less popular, more expensive, like the Stratasys Ultim material, which is a polyether imide material. So it's, and I think of this as it's sort of like a moving hot glue gun. So we're squeezing out the polymer and just moving the nozzle around to build the part. And we can make some nice parts this way. This shows some of the some sample parts from the internet. The first company to commercialize this technology was Stratasys. It was formed by Scott Crump and his wife Lisa, and he's now retired. But at any rate, it's great for plastic parts. There's at least one commercial technology for producing metal parts using extrusion. This is a company called Mark Forged in the U.S., and I'm assuming that they use a binder and then burn the binder out and do subsequent sintering, maybe not dissimilar to metal injection molding technology. So this is the example of that. And again, there's probably maybe 200 companies that now produce this kind of equipment. Generally the properties are not the best. ABS is a good material. The Ultim material is very good in terms of properties, but the general materials, the PLA, it's not particularly outstanding in terms of the properties. So we see there are some service applications for this technology, but generally these are for what we call form and feel, sort of something to look at, but not necessarily to expect particularly good properties for applications. Now the next one is binder jetting. I mentioned this was the original 3D printing. Came from MIT. Ellie Sachs and Mike Sema were professors there, and they developed this technology in the very early 1990s. And it's with binder jetting, there's typically an XY gantry with print heads. And the print heads, the big advantage of this technology is that we can use all of the information and all the experience that we have for doing 2-dimensional printing with inkjet printers. We can use that same kind of technology here because we're simply squirting a binder down from effectively an inkjet printhead into a powder bed. The binder glues the powder together where it lands, and then of course the powder remains loose everywhere else. And so we can build parts this way. The parts are very frail typically. They're very weak, as you might imagine, and so for applications to get service project properties, these parts are typically go through a post-processing step where the binder is removed either chemically or thermally, and then at this stage we treat the part exactly like a powder metallurgy part with relatively low density, and we do the usual techniques to center the part together. So the commercial technologies, the popular ones I'm aware of here for doing metal parts this way, there's an old company X1 that's been around for a long time. A newer company, Desktop Metals, is relatively new and also uses this technology for doing metal additive manufacturing. Yeah, and I think I have some parts here. Yeah, so there's some parts. One of the big advantages with polymers of this technology is you can see we can do colorized parts because it's very simple to adopt color printers where we have multiple print heads with separate colors. That technology is already well established, and we can use that to print not only the binder to hold the part together, but also the color. So we can colorize the parts this way. And this has historically been the big advantage for this, is being able to make colorized parts. Again, it's not done with metals, it's done with polymers. The original company to spin off this color technology was a company called Z Corp out of Massachusetts, not far from MIT. And that company has now been sold some years ago, I think maybe to 3D Systems, but I'm not sure anyway. The company, I don't think, Z Corp, if they exist, it's in name only. Okay, sheet lamination, this is an old process, right, we know from the earlier lecture, but this is a technology where we take sheets of material and bind them together to form an object. So we see here the main aspects. In this case, this is based on an old machine by a company called Helicis that used a laser. This technology that was the company name for this process was Laminated Object Manufacturing, or LOM, and it involved a laser that would scan a surface. It would scan hatches to cut the paper. It was butcher block paper that was used, so it's just regular paper on a spool that would come up. There was an adhesive that was applied to the paper. It was pressed down onto the build platform here, and then the cutters came through to outline the part, which would be the white circle on this photo, on this schematic. But it also had to hatch everything else, because at the end of the day, we had to be able to remove all of that paper away from the part. And so to facilitate that, the paper was chopped up into pieces effectively by this crosshatch pattern. The LOM parts, again, the company went out of business in the early 1990s. Helicis, Mike Fagan, who ran Helicis, is still around as far as I know. I've seen his name on programs from a few years ago. Helicis was actually the first modern additive manufacturing company to be established. He beat Chuck Hull and 3D Systems by 1 or 2 years. But he was the first company to form, but he was not the first product to be shipped. So he had trouble getting his machines put together and commercialized. So while he was ahead of Chuck in forming the company, he was behind Chuck in terms of putting the first machine out. So, and another issue, if I could take the opportunity to tell a short story about Mike Fagan, who really did the original inventing here. It turns out there was an interesting story with a moral for graduate students. So particularly, so the story is this. This is what happened. Carl Deckard at the University of Texas is credited with inventing powder bed fusion, laser sintering. We'll get to that in a minute. But it turns out that when he applied for the patent, which was issued in, I think, 1987, for laser sintering, at the patent office, it turns out there was a dispute. And the dispute came from Mike Fagan, who said that he actually had invented laser sintering. And so with the patent office, the way that they resolved these kinds of disputes is they said, well, they basically, to both individuals said, well, give us your earliest documentation that shows when you invented it, if you have it. And we will use that as a basis for determining, who the inventor was and who gets the patent. And so they went through this process. It turns out Carl Deckard, he was a little kind of quirky. He was a little strange. In some sense, in a good way, in some sense, not so good. But in a good way, one of the things that he did as he was developing laser sintering at the University of Texas is he kept bound notebooks where he would keep his research, and he dated every page of the notebook so that he had this. And so when asked to provide this kind of information, he was able to provide earlier dates of development than Mike Fagan was able to provide. And so it doesn't matter whether Fagan invented it first or not. It was Carl that was able to prove with a date that was earlier than anything Mike Fagan could supply. So Texas got the patent, and Carl Deckard got the recognition for the invention, and Mike Fagan was sort of, left outside in the dark, at least with respect to laser sintering. But he did do he did do this process. The company produced a number of these machines, and they made beautiful parts because the laser, as it scanned the surface of the paper, it would kind of burn it a little bit, so it had sort of a brown color, and it was laminated, so the parts came out. They really looked very much like natural wood. And so they were just beautiful parts, like they were carved out of wood. And I always enjoyed the parts myself. But there was a problem, which maybe it was an urban legend. I don't know. But at any rate, it was reported that the laser sometimes would catch the paper on fire, and it would burn, and they'd have these terrible fires in the machine. And there's nothing that can kill a technology like having to put out a fire, in your machine that's uncontrolled. And so we think that was the case here, perhaps. And so the LOM process disappeared. They were only produced these machines for 4 or 5 years. But other companies have come along behind that instead of using the laser to cut, they actually use a knife, a mechanical cutting blade, to cut. This was the innovation of the M-Core machine that I showed, where it had the little colorized human head. That was one of the company principles, the one that uses laser print paper as the feedstock. And so they don't have a laser; they just use cutters to make these. There is one other thing I should mention about sheet lamination. Is there's another technology that that falls within the additive manufacturing world called ultrasonic additive manufacturing, UAM. It's a very popular process. It was developed, I believe, at the Edison Welding Institute at Ohio State, I think. Certainly that's where the company came out of there. It was Fabrasonics, I think is the name of the company now. that does this. And what they do is they take a thin piece of metal foil and lay it down over a build surface, and then come in with an ultrasonic, with a sonotrode, which is basically a vibrating cylinder. They roll it across the foil, and it actually mechanically welds it, solid state welds it, to the previous layer. And so they can use this to build layers without geometry, but then every few layers, they come in with a milling head and they machine out what the surface looks like. And so, yeah, you can kind of argue whether it falls within the world of additive, but we've included it in the fold. So, but anyway, one of the big advantages of this process is it's the only additive process that I'm aware of where you can do some remarkable things because it's a process that takes place at room temperature. There's no heat involved with this process. So, for example, if we want to embed a plastic sensor in the part during the build, we can do that, and we don't worry about the heat from densifying the metal causing any damage to the part. And so we can do these kinds of things with this sheet metal with this sheet lamination technique. So so that's that part. This again shows some of the technologies. These are all parts. They come from various web sources. Most I recognize come from the MCore website. But you can see they make spectacular parts that are colorized, and it's really very nice technology for that purpose. This is the oldest technology, vat polymerization. I showed you some early precursors to that from Japan and the United States. And of course, Chuck Hull was the first one to get a machine out the door in 1987. For those of you that don't know, this technology, I can show you some parts here. Yeah, the parts are quite beautiful. They're lovely parts. That polymerization has the advantage of typically producing the best surface finish out of the machine. And you can see that here. You know, these are quite detailed and quite high quality parts in terms of the finish. The materials are typically epoxy polymers, liquid resins that are in a vat, hence the name vat polymerization. The properties, the mechanical properties of these parts are not very good. The epoxies after cross-linking are relatively brittle. They just snap. And so to use this for structural applications requires that the part go into service really with no mechanical load. And so that limits the process considerably. But at any rate, what happens with this process, we have a vat of unpolymerized resin liquid. Again, some acrylics, but typically epoxies. And there's a platform, and then we have a low power laser. This is a milliwatt laser. So we're not relying on the heat for cross-linking, but rather the wavelength of the laser will activate the resin and result in free radicals that can join together and cross-link to create the solid part. And so we build on this platform. During the process, the platform goes down, and liquid is coated up on the top, and then the process is repeated. So, and then typically all of this stereolithography or the resin, the parts are typically built with these complicated scan strategies, so that there's a lot of unpolymerized material. So effectively, you might imagine that the part is built with various chambers of liquid photopolymer that are surrounded by walls of the polymerized material. And the reason that this is done is a time factor. Rather than using the laser point source to scan every single area of the part as it's built, they can just scan a very small section and keep the polymer in liquid form entrapped. And then they take the part after the build, and they put it in an ultrasonic oven and just bathe the entire part in the proper wavelength of light. Again, it's ultraviolet. And and that in that way the part can be polymerized. That's much faster than relying on the beam to polymerize the part. Again, these parts are they're spectacularly fine detailed, and the surface is very smooth. It's again the smoothest of the parts that we see. And as a matter of fact, I should mention as well, there are post-processing technologies that make the part even smoother. One example is we can take a stereolithography part out of the machine, cure it, and then there's some commercially available paints. The most popular being clear coat, I guess, that I'm aware of. It's called clear coat paint. You paint the surface, and the thing turns almost literally into a glass-like transparency. And I don't think, neither of these parts show it. Perhaps, maybe right here, this may have seen some finishing, but again, it's not this milky white surface that's translucent. I mean, it literally looks like glass. It's a spectacular finish. Okay, multiple material jetting is the next one. This is where we actually are jetting the feedstock onto a platform. So it differs from binder jetting in that respect, where binder, I'm just squirting down glue, where here I'm actually squirting down the feedstock material. And again, it's most popular with the epoxy resin. So the feedstock is very similar, if not identical, to the vat polymerization material. And the distinction being that in this case, the liquid the unpolymerized material is up here. It goes through a nozzle which, with this charge driver, that produces droplets. And then the droplets are squirted down to the substrate here to build the part. And it's this area down here that's completely bathed in ultraviolet light. So the droplet splats on the surface, and it's immediately polymerized by the UV light. So one of the, and of course you see here this droplet catcher. The way these machines are typically designed is the droplet feeder. This design here, it's easier for it simply to run all the time and create droplets. And when you want to stop it, they just mechanically, move something in place to capture the droplets. And so they work the technology this way. I can show you some parts. I guess I have this here. So here's some various parts from various sources that show, again, reasonably on the parts with, they're produced this way. We also can, it's possible, only in the last 5 years or so, to use material jetting to print metals. And I think there's at least one company now that is liquefying metal, which, easy to melt, and then it's producing droplets and squirting the metal droplets down onto a substrate. And so we can produce, parts that way. I can't remember the name of the company or where it originated. Which one? Okay, right, okay. It turns out I always think of Melissa Orme, O-R-M-E, who back in the early 1990s worked all the physics out for metal droplet formation and for jetting droplets. And so that theory and the physics of that process were well understood as they would apply to additive manufacturing many years before the company came through. Melissa Orme, she was in Southern California, and she wound up at Boeing. And so, and indeed, here I think even now today, she basically is responsible for all the additive manufacturing work at Boeing, which is significant, obviously. So she's done very well. Okay, the next one is well, obviously one I think this is the subject of the focus of this short course is directed energy deposition. In this case, obviously we know about this, but it's very there are a lot of different variations on this, maybe more so than the other technologies, because we have a variety of energy sources. Typically, and again we'll talk about this later, laser beams. We also have electron beams, and we also have like electric arc type processes, both standard arc and plasma arc technologies. And the feedstock can come in a variety of ways. This shows the feedstock coming down a tube in powder form into the work area. But it's also possible to have a nozzle and to feed powder feedstock from the side, or also for certain technologies a wire feed and to feed wire down. In this way we can produce large parts very quickly, because the wire feed DED is the technology that has the highest rate of material deposition of all of the additive technologies. So we can produce big parts, for example an airframe, fairly quickly, because we're depositing material at at multiple kilograms per hour feed rates, rather than for the other processes where we're maybe feeding fractions of grams or fractions of kilograms in an hour. Very small, very low feed rates. Yeah, and so this shows a part. The original, I guess the original developer of this technology was David Keischer at Sandia, I think Sandia National, it's Los Alamos. It was Los Alamos, yeah, in New Mexico, in the U.S. And he spun off. The first company was Optimec here that produced the first machine. Optimec is still in business. They're still making the machine there. They call the machine the lens machine, laser engineered net shaping, and so the lens machines, they're still out there, still available, and so it's a nice success story. So here's powder bed fusion is the one that, of course, is closest to me. It was in the inventor was credited to be Carl Deckard. He's the one that got his name associated with the technology. He was a master's student at the University of Texas. I credit Carl with my becoming involved in additive manufacturing, because one day he showed up at my office. I was a young assistant professor. I'm sure I was working on something important. He just showed up out of the blue and said, "Hey, can I talk to you for a second about my research project?" And I fortunately said yes, instead of shooing him away. So he came in and talked about this technology he invented. He was sort of a hardcore mechanical engineering kind of student, didn't really have a strong background in materials, and so he was really looking for to get answers to materials questions. And so it was from that day that I started, dealing with additive and became involved. Carl was an interesting person, and there's an interesting story about Carl Deckard, who's the credited inventor of laser sintering or powder bed fusion, and Ross Householder, who was someone who I mentioned in passing on the history part. Ross Householder in 1979 patented what looks exactly like laser sintering. I sort of blasted through the slide from the Householder patent. But he basically invented laser sintering. Ross did, Householder, 8 years before Carl got his patent. And just as a side story from the main story, what happened this was discovered by DTM around 1994, 1995. They discovered the Householder patent, and they were very concerned because their entire company was based on the Deckard patent. And so they found this, the company was threatened by this earlier knowledge. And you have to appreciate that back in those days, you couldn't just do a Google scan of patents and get everything. It had to be done by hand, and so it was easy to overlook patents, particularly if the title of the patent was rather obscure. So anyway, so it was missed, but then discovered. So what the company did is they located Ross Householder. He was in New Mexico, and they rushed out and made him a deal and bought his patent rights, so the company could be safe. And one of the impacts of that, if I could talk in a selfish way, is the DTM was paying royalties to the University of Texas at that time because they had licensed the technology, thinking that Carl invented it. So what they said is, well, it cost them, I think it was about $250,000 to buy the rights of the householder patent. And so they came to the university and said, we're going to give the university the opportunity to pay this $250,000 fee because it protects your patent as well as the company. And so the way that was done is DTM stopped paying royalties to the university for about a year to recover that money, which meant that the university did not get their share, but it also meant that the inventors, and I was one of them, we didn't get our share either. So it's a painful memory of this debacle from those days. Now, the footnote of the story is this. This is something for you to consider, and that is, in 1979, Ross Householder had his patent. In 1986, Carl had his patent. So guess where Ross Householder was living in 1979 through about 1984. He was living in Austin, Texas, where Carl Deckard was, which is a remarkable coincidence. And so while Carl absolutely angrily insisted that he had never met Ross Householder, I sort of have this wildly speculative vision that would be consistent with Carl, that he would be in a bar, drinking a beer down on 6th Street in Austin, which is our popular entertainment district. And he winds up sitting next to a guy and they start a conversation about powder bed fusion. And he happens to have a meeting with Ross Householder. Carl thinks this is a great idea, and then he goes off and copies it. That's completely undocumented. It's wildly speculative, but it just seems weird that Householder would be living in Austin, where Carl was, at the same time when he invented the process. So anyway, it was all like, as we say in academia, it's all academic after that. Ross sold his rights to the university and to the company. He was very happy. I think he built a restaurant with it. And we were happy because we have our technology protected. No one else has appeared in the meantime to challenge those original patents. And about 2009, 2010, the patents all expired anyway. So now it's an open market. Yeah, so I was only able to enjoy the royalty stream from about 1991, 1992 until about 2007, 2008. But it was nice. It didn't make me rich, but it helped put my kids through college. I guess that's a good thing. So anyway, so that's the powder bed fusion story. And again, here's the parts that we can produce. There's one significant advantage. And again, I'm biased to laser to powder bed, but there's one significant advantage for powder bed fusion of polymers, and that is the parts, because the parts are built at high temperature in a powder bed, there's not a requirement to include support structures. And if you've ever had a job of removing support structures, you can appreciate that this really is kind of a big deal. Because what it allows us to do is, for most build processes in additive, we have to have a support structure to hold the part in place during the build. And if those supports have to be removed after finishing, I have to be able to mechanically get to the support with enough force to break away the structure and remove it. However, with powder bed fusion, the support structure is the loose powder. So with laser sintering or powder bed fusion of polymers, all I have to do is I just have to be able to shake out the loose powder, and I can produce the desired part. So really the only kinds of objects that we really can't build very easily would be like a hollow sphere that's completely enclosed, because there's no way to get the powder out of the inside. But again, these are very limited cases. And for the most part, we can produce, very nice geometries in materials with, again, without the need to remove the support structures. And also, this has a beneficial effect on the surface finish as well, because the support structures leave behind surface artifacts, which do not appear with these parts. And then lastly, of course, nylon is a classic material, a feedstock for powder bed fusion in polymers. And nylon has actually reasonably good service properties in terms of the mechanicals. And so it's a very good part for service objects as well. It turns out one of the, I've covered material extrusion. It turns out that one of the rules of material extrusion and powder bed fusion is the feedstock, the polymer feedstock. If it works for one technology, it generally does not work for the other. So, for example, ABS and polylactic acid for the extrusion machines, as well as the polyimide, the ULTIM material, those are all amorphous polymers. And we like amorphous polymers for that process because we're melting and flowing, and we'd like for the, like to have a range of temperatures where the material has varying viscosity, because we don't want it to be too viscous or it doesn't flow. If it's too liquidy, then it doesn't stick where we want it to. So amorphous polymers work great there, but they don't work in powder bed. Whereas in powder bed, we like crystalline polymers, which have they behave like a metal, a very sharp melting point, very sharp solidification point, and that's what works well here, but doesn't work very well in extrusion. So typically, for polymers, they work for one or the other, but not both. So, okay. All right. So that takes care of the of the survey. So now I want to move into specifically to directed energy deposition. So finally, at last, here we've arrived. There are, again, as I mentioned, there are three general types of process in terms of the difference is the energy beam that's used for directed energy deposition. This comes from EWI. It's the Edison Welding Institute in Columbus, Ohio. Again, they're associated with Ohio State University. But the first one is we can use lasers as a power source. And you can read about it here, but basically it's a matter of putting the feedstock in the path of the laser and to build this part. We'll talk about the advantages and disadvantages of these in a moment. I have a slide on that. But for now, we have that energy source. The second one uses an electron beam energy source, and we call the laser beam DED-LB. The energy beam DED-EB is typically the way it's written. And again, this is consistent with 52900. So then we have, so basically we can use this for manufacturing. Again, you can read a little bit about it, but that's the second source. And then the third one is the arc-directed energy deposition, DED-A, which again uses basically a weld head of some sort to move and to deposit material in that respect. Again, it's the classic Baker patent from 100 years ago is the third of the technologies. We have, this shows the various beam types in more of a schematic form, as well as the feedstock delivery. So really with directed energy deposition, all of the variations deal with the energy source and the feedstock deposition. So here we see the first one is the laser-based machine with the feedstock, comes in here typically from as part of the nozzle. We have the energy beam, electron beam, where again it's an electron beam, and typically the e-beam processes use a wire feed. And again, the difference between wire and powder is primarily the deposition rate. We can deposit material much faster with a wire than we can with a powder. So then the third one, the rest of these are all variations on arc welding, and again, fairly traditional sources. You know, the first is the gas metal arc welder, where in this case if there's an electric, all of these are electric arc, but the feedstock is actually also the arcing material. So the metal wire that creates the arc results in the melting of the feedstock and its deposition. For tungsten arc welding, so here you can see the metal coming down and being deposited. For gas tungsten arc deposition, this so-called GTA, what we have is up here is a tungsten electrode, just like TIG or tungsten inert gas welding. The electrode is permanent; it does not melt. It maybe abrades, but it doesn't melt. And the arc is created, but then we have to provide the feedstock separately. And again, in this case, often it's a wire feed that comes into the path of the arc to deposit the material. And then finally, we have the plasma arc directed energy deposition, DED-PA, where in this case, the geometry of the nozzle is designed to intensify the energy source to create a plasma arc. And and again, this is a permanent electrode. I guess it's a tungsten electrode. So the distinction between these two is the design of the nozzle, where this one produces a more intense beam or heat source. Okay, well, let's talk a little bit about lasers. I want to say a little bit about that. This shows for lasers the span of electromagnetic radiation. Lasers themselves sort of fall in this range here, which includes the visible range. I think the majority of lasers used in additive manufacturing, whether it's vat polymerization or powder bed fusion or directed energy deposition, are all ultraviolet lasers. I guess there used to be some YAG lasers out there for powder bed, but typically they're all ultraviolet. Part of the reason is that they're in the laser world, I think they're relatively cheap in terms of the cost per kilowatt, as it were. So this is the history of the development of lasers. And by the way, you know, lasers, the first laser came out in 1960, and so you know, it becomes an enabling technology for a lot of additive manufacturing, right? If we don't have the laser, you know, you don't have the technology. So along with distributed computing, with desktop computers, this also is an important step in the development. This is the reason why we don't see these technologies developing earlier. So anyway, yeah, it was Mayman at Hughes Research that first demonstrated in 1960 a Ruby laser. Then we see over here. This shows the material used in the laser and the year of development of that. And so if we come down here to the sort of the UV world, you know, we see the CO2 lasers down here. And again, for manufacturing, we have to have power. I mean, it's the energy deposition rate that must be high to do to use lasers in manufacturing, whether it's for additive or something else like cutting or welding with lasers. And so that kind of limits the lasers to this group. And again, the preponderance are CO2 lasers. Although I think I recall for metal processing, there's what, some diode lasers? Yeah, yes, diode lasers that are used because I guess the coupling is better. YAG lasers in the early days, I saw like YAG lasers. I haven't seen them much lately though. So, and then of course excimer lasers. These are the ones that have the power capability to be able to produce, to really make an impact. This is a plot that shows the power density of the laser versus the interaction time, what the exposure of the laser on the part is. And it shows really all kinds of laser manufacturing. So we have shock hardening, melt quenching, drilling, various kinds of melting. And notice that additive manufacturing is way down here. LAM is laser additive manufacturing. And we are very low, relatively low powers, around say 1,000 watts per centimeter. And we are very long interaction times, a tenth of a second-ish, as opposed to, 10 to the minus 8 seconds. So it's so we're down here at the very, very end of the range for that technology. So let me show you a couple of these technologies, or what they look like, at least schematically. This shows an electron beam version with a wire feed. This part came from SEACI, which I think is a California-based company that builds these parts. I think we'll see in a future lecture. I have maybe a video, but certainly some photographs of parts made this way. And it's possible to deposit massive quantities of material very quickly with the SEACI process. So it's used, I think, primarily, in aerospace. So building wing sections and things like that, very large parts. I would mention as an aside that it doesn't make intuitive sense, but it turns out that if we look at issues like the environment and energy uses and sustainability, if we enter that world of in terms of manufacturing, what's really the most environmentally friendly, what makes the best use of the energy, it turns out that actually this technique is the best among the additive processes. There's a plot that was created by an MIT professor whose name was Gutowski. So we call these the Gutowski plot. And what the plot shows is for virtually every manufacturing process, not just additive, but everything, it says that the energy required per unit mass to create a part using that manufacturing technology is inversely proportional to the build speed. It's a very simple plot where you plot the energy needed versus the build speed or the build rate, and the plot goes like a 1 over x plot. So it's the way to be energy efficient in manufacturing is to deposit material very quickly. And so this technology, the additive technologies that build quickly are way out on the curve and are very energy efficient. The rest of the processes, which is most of the other additive manufacturing technologies, actually kind of lie in the middle. They're not all the way at the bad side, but they're kind of in the middle of the curve, and so they're not nearly as energy efficient in terms of the usage and the utilization of the energy. So anyways, that's this process. This shows what a plasma arc DED might look like. This came from a paper, but basically we have the weld gas sources goes to a control console. There's a shielding gas that comes down, the orifice gas. Again, this is for plasma arcs. So we have the constrained beam here that produces the plasma. So it creates a plasma source as opposed to an electric arc. And then in this case, they can come in with gas transport gas, in this case argon, and we have the powder feed that feeds down through this outside sleeve down to the part so that we can deposit the material. So obviously coolant unit is needed, as is the case for most metal processes, and we need a power source, which is of course the case for virtually all the metal processes in additive. And can we produce a part this way? So I enjoy this plot. It's a plot that I reproduced from ASTM F3187. It's the standard guide for directed energy deposition of metals. And what they show, actually, if I could again take a small aside here, on this standard, the way that standards are developed in ASTM, it's a very democratic process. So basically, the standard is written by a work group. In this case, it was a bunch of obviously DED manufacturer representatives, and that standard, that draft, goes to the entire ASTM F42 committee, which now numbers almost 1,000 people. But it goes to that committee. I'm of course a member of that group. So this standard, when it was being developed, the draft came to me and I read it, and I didn't like it. And the reason I didn't like it is because it read like an advertising brochure for DED. It was basically, our process is wonderful and everybody else's process stinks. And I said, this is not really the way the standard should be written. I mean, feel free to make your case, but you don't have to bash everybody else in the process. And so so it turns out that the way that the procedure works is if any individual that has voting rights in ASTM can vote negative. You either pass a positive vote or a negative vote. And one person casting a negative vote stops the entire process. And until the committee comes to some kind of agreement with the person who voted negative, they can't. The standard cannot move forward. So there were other people that voted negative too. There always are multiple people vote negative on these. So they have to work with us. And so the DED people, it was this guy named Grillis that wrote this, Don Grillis, I think. He worked for Optimac in New Mexico. He and we went round and round on this because he would basically say, okay, we'll fix it. He'd fix it, he'd send it to me. I go, I still don't like it. And so they have to go back and fix it. And this went, I think I saw this standard maybe half a dozen times. And I kept telling him, I said, no, you're not doing what you say you're doing. And so they finally got rid of the pejorative language and came out with, I think, a standard that's actually very, very good. Okay, so having said all that, this is, I think, a very useful table for distinguishing between the laser energy source for directed energy versus the electron beam versus the plasma arc or arc type processes. And what it shows is for these types of factors, the build volume, basically how big the part is, the resolution of the part surface, how fast we can deposit, the coupling and efficiency, that is, how well does the energy beam couple to the feedstock, which is important from an energy perspective. Because if the coupling is poor, I have to spend a lot of energy to get a little bit of a part created. And then finally, the potential for contamination. And so they have this chart that shows basically you want to look where the highs and lows are. And so what we see is the places where the laser-based processes tend to shine is, first with build volume, but also with the detail resolution is among the best for the laser-based processes. So if we're concerned about the feature size, then that would lead us towards selecting a laser-based process as opposed to some of the others. Again, the downside is the coupling efficiency is pretty bad because lasers typically don't couple very well to materials. Having said that, we have an advantage with powder bed because we can get mechanical coupling because even though a laser may couple to a metal with, say, maybe a 20% efficiency, if I have a powder bed, what happens is the laser can come down and it sort of it penetrates into the powder bed, and then it kind of rattles around it. 20% gets absorbed, 80% gets reflected, but that 80% goes and pops against another powder particle and supplies 20%. And so because the laser beam sort of bounces around in the powder bed, we can actually get better coupling, which is this realization was one of my great failures at the university, because Joe Beeman, who's a professor at our place, he was Carl Deckard's supervisor for his master's work when he invented laser sintering. Joe wanted to build a metal powder-based metal machine, which he did. But you have to appreciate, nobody's done this before, right? There was nothing really to go with. And so he came to me, since I was the materials guy. He said, how big a laser should we buy? Because we didn't know at the time. I mean, there was no comparison machine. And so what I did is I looked up the couplings and did the calculations. I said, you need a kilowatt laser. Well, those of you that work with metal additive, you don't need nearly so much power. And my error was I didn't appreciate that the beam bounces around and couples mechanically. And so Joe spent an enormous amount of money to buy the 1 kilowatt laser when he only needed about 250 watts. And so he never let me live this down. He always brought up, yeah, right, you really screwed up on the laser. And he was completely right. So anyway, so that's the issue. Moving on, though, the build volume, the electron beam, the Siaki type processes is really where the electron beam shines here, and with the coupling efficiency, because the electron beam couples very well with metals. It's also very good on deposition rate, as good as we can get in depositing materials. So those are the errors, but it suffers the details, right? So basically, with these processes, and this is true for really all of manufacturing, if I want to dump a lot of material quickly, I usually suffer on the detail and the resolution. And that's true really for almost any process, certainly true for additive. Moving on to the plasma arc technology, it does very well with the coupling efficiency. It's pretty good on the build volume as well. And again, the deposition rate is pretty good as well for these. So this is, I think, it's a nice table in the standard for dealing with selection. And again, I highly recommend the standard to you as well. It's if you're interested in directed energy deposition, it's a very useful standard. So, well, we're about an hour in, and I think probably it would be a good idea to take a break. I'm ready to move on to the next topic. So it seems like a good point in the program to take a break. So why don't we maybe take a 10-minute break? We'll be back here at 3:45, and I'll pick up energy deposition. Okay, so let's